Welcome back to the course of chemical crystallography. In the previous lecture, as if you remember, we were discussing about Bragg's law and its applications, and we were trying to understand the choice of radiations for different purposes, and in that we identified that if you use copper K alpha radiation, you can achieve a maximum resolution of 0.77 angstrom, while if you want to use molybdenum radiation, you can achieve a very high resolution of 0.35 angstroms. So with this, I would like to continue in this lecture and see what happens if we try to use these different radiations for different purposes. Suppose if we are trying to do a powder X-ray diffraction experiment where we are going to record a PXRD data, which generally we obtain as intensity versus 2 theta plot, and as we have already indicated, something like from 3 degree to 80 degree we measure in 2 theta, and what we see are sets of peaks, and these peaks correspond to every Bragg reflections which correspond to the diffraction, which satisfies the Bragg's diffraction condition. So every such reflection is identified with unique H, K and L values. And we have also seen in case of cubic system how those H, K, L values can be identified, and from that how one can determine the unit cell parameter, and then also you can identify the lattice centering. Suppose in this particular case which I have drawn here, the peaks that has come in this diffraction pattern ranges from about 5 degrees in 2 theta to about 70 degrees in 2 theta. And this, suppose I have recorded using copper K alpha radiation. What is the wavelength of copper K alpha? It is 1.5406 angstroms. So now if somebody wants to use a molybdenum radiation for the same purpose, what should happen? So suppose for lambda copper divided by lambda MO, that is, I am writing Bragg's law in two different wavelengths, which would mean DHKL sine theta for copper by DHKL sine theta for molybdenum. So now, since the crystal is same, the D values are going to be same for a particular reflection, so they can be cancelled, and what we end up is the sine theta copper versus sine theta molybdenum is just a ratio of the corresponding wavelengths. So if I try to calculate this ratio, 1.54 approximately divided by 0.71 is equal to sine theta for copper by sine theta for molybdenum. So now in this particular data where we have the first peak coming around 5 degrees in 2 theta, for copper. So for the first peak we can write 1.54 by 0.71 equal to sine 2.5 divided by sine theta molybdenum. So for this situation, for the first peak that we found, the theta MO can be calculated as, which means 2 theta MO is 2.3 degree. Note this number. Similarly, the last peak for copper K alpha radiation is at about 70 degree into theta. So now again we apply the same method at this last peak. So 1.54 divided by 0.71 equal to sine 35 by sine theta MO, and then if we solve for theta MO, we would get theta MO as equal to 15.33 degree, that is 2 theta MO as 30.66 degree. So the data which was collected using copper K alpha, data with copper K alpha, it spanned from 5 degree to 70 degree into theta. But if we collect with MOK alpha radiation, the same data would span from 2.3 degree to 30.66 degree into theta. What does it mean? It means the powder pattern, which was quite broad over a range of 2 theta using copper, is now squeezed in a small region of 2 theta, and it appears as if the peaks are very close. So what can happen in this case is that the two peaks which are having very similar d values, the difference in the 2 theta value for their diffraction angle will be very close, and in many cases those reflections can overlap with each other and we may miss some important reflections, and two reflections or more reflections can merge together to give you one peak if you try to use molybdenum radiation. So the entire pattern is going to be squeezed. Until and unless we use a very high intensity synchrotron radiation for this kind of applications with a very small wavelength, we cannot actually segregate these reflections appropriately with a smaller wavelength. So as a result, we generally use copper K alpha radiation for recording powdered X-ray diffraction data, whereas in case of single crystal X-ray diffraction, when the diffraction spots appear at different places of your detector and they are all well resolved at all possible angles, we use molybdenum K alpha radiation to achieve higher resolution with your given crystal. So what we now know is that the Bragg's law applies to a set of planes which we imagine to be inside the crystal lattice, and those planes contain a number of scatterers, and those scatterers are responsible for X-ray diffraction. But if we look at the Bragg's law, it shows that n lambda equal to 2 DHKL sine theta, which means the sine theta, which is the measure of diffraction of the X-rays, is inversely proportional to the interplanar spacing d. So this sine theta being inversely proportional to d gives you an impression that there is some reciprocality in it. and theta being the measure of deviation of the diffracted beam from the direct beam, we would like to get a direct relationship between sine theta and d. So, because of this inverse relation, the structures with large d, that means structures with large unit cells, will exhibit compressed diffraction pattern and vice versa. So, to replace this inverse relationship and to establish a direct relation between sine theta and d, the concept of reciprocal lattice is conceived. Let us see what do we mean by a reciprocal lattice. On your right, we have a two-dimensional lattice which is adapted from Stout and Jensen's book. Here, let us consider that the lattice point O is considered to be the origin of the lattice, and let us consider normal to all the direct lattice planes HKL from this lattice point O assumed to be the origin. So, what we have here is the plane going like this, which we have Miller indices 0 and 1 is one set of parallel planes, and then the plane which is going through the middle of this unit cell is having Miller indices 1, 1. The plane which starts from this point and goes through the second unit cell edge corner and continues is termed as 2, 1, and the one which cuts the third unit cell is called as 3, 1. So, we have 4 sets of different direct lattice planes drawn here. So, what we try to now do is we are trying to draw perpendicular from this reciprocal lattice origin to each one of those planes, that is 0, 1, 1, 1, 2, 1 and 3, 1. So, we are drawing these normals. So, from O, this is a normal, that is a perpendicular drawn on 0, 1. This line is a perpendicular drawn on 1, 1. This line is perpendicular drawn on 2, 1, and the fourth line is perpendicular drawn on 3, 1. So, now we are drawing, after drawing these perpendiculars to those direct lattice planes, we terminate each of these perpendiculars at the points marked as star at a distance equal to 1 by dHK. That means the distance between the set of 0, 1 planes is d0, 1. So, we cut it at 1 by d0, 1 distance from the reciprocal, from the origin O. So, now as we find in this 2D lattice, we now have points 0, 1, 1, 1, 2, 1 and 3, 1, which represent individual lattice planes in the direct lattice. So, what has happened is that the planes, the crystallographic planes containing scatterers, atoms, are now considered to be imaginary points in space, and these imaginary points are now called the reciprocal lattice points, and the network that can be generated using those points is called the reciprocal lattice. So, what is happening is, in this particular case, we have a two-dimensional network and then we have a set of planes. I have one fixed origin, and from that fixed origin I am dropping perpendicular to each one of those planes, terminating the perpendicular at a distance 1 by dHKL, and then the point of termination is marked as a point which corresponds to a direct lattice plane. So these lattice planes are now converted to lattice points in the reciprocal space, and that is why these are called reciprocal lattice points. And if we construct the same in 3 dimension, it will generate a network, it will generate a 3D network, and it will be called as reciprocal lattice. So now let us consider the drawing here, once again adapted from Stout and Jensen's book, page number 27. So taking the direct lattice point O, so this point O is a direct lattice point O as the origin, and the distance OA as the unit translation along the axial direction x. All the lattice planes which has the Miller indices 0 will be parallel to OA. That means if you have one axis like this pointing from me towards you, and then any plane which is parallel to this axis, be it here like that, or be it like this, or be it like that, in any direction, any reciprocal lattice, any direct lattice plane parallel to this axis will have their H index 0, because these planes do not meet the axis x. So if we have such planes which are parallel to x axis, then if we draw perpendicular from O, their normal will be perpendicular to OA through O. That means the perpendicular that we draw from the origin to this will be perpendicular to OA, which is along the x-axis. And all these reciprocal lattice points, suppose you have a plane parallel here, then a plane parallel there, and a plane parallel there, and a plane parallel there. These are all parallel planes at a given distance from the axis OA. If we drop perpendicular from this point in the origin to these planes and cut those distances at 1 by d, all those reciprocal lattice points that would generate would fall on this line, which is marked as 0 star. Similarly, all the direct lattice planes with h equal to 1, which means the direct lattice plane is now passing through A and goes like that, which has the h index of 1, other two indices can be k and l, which is written here as well, 1kl set of planes. If we drop perpendicular to those 1kl set of planes, which is shown here, and we terminate each one of those normals at a distance 1 by d1kl, at 1 by d1kl, they would come and fall on a line which is marked here as 1 star. In the same manner, the planes which will pass through the midpoint of OA, which is A by 2, the plane which I am drawing in green is marked here as well. It is a 2kl plane. So the normal from reciprocal, this direct lattice origin O to that is then terminated at one place, which once again falls in the line marked as 2 star. So, if we try to apply a simple mathematics, what we can find is D1KL is equal to OA sine phi HKL, where phi is the angle here. So, D1KL is equal to D1KL is the distance from here to there, and that distance is nothing but OA sine phi 1 or sine phi HKL, which actually should be 1KL. And similarly, OB is a distance which is 1 by D1KL, right? We cut this normal at point B, which is at a distance 1 by D1KL. So, OB is equal to 1 by OA sine phi 1KL. So, now if we want to know what is the value of delta 1, which is delta 1 KL, is nothing but OB sine phi HKL, or rather sine phi 1 KL, because if that angle is phi 1, the angle here is also phi 1. So, now if we compute OB sine phi 1 KL, it is equal to 1 by OA, because OB equal to 1 by OA sine phi 1 KL. So, OB sine phi 1 KL is nothing but 1 by OA. In the same manner, one can show that delta 2, which is this, is equal to delta 2 KL, which is equal to OB sine phi 2 KL, which is equal to 2 by OA. So, for a general HKL reflection or NKL reflection, where n can be 1, 2, 3, 4, anything, in general, delta n is equal to delta NKL is nothing but n by OA. This indicates that the reciprocal lattice points having a particular index h, k or l as fixed, and then if we vary the values for other two indices, in this case we are keeping h fixed. So, 0KL means we can vary k and l, 1KL means we can vary k and l, 2KL means we can vary k and l. So, two other indices can be varied. What it generates is that sets of reciprocal lattice points falling on the lines drawn as 0 star, 1 star, 2 star and so on. And this is considered only in one direction, that is the direction of OA. The same can be considered in all the three directions. So, when you expand the concept in all the three directions, what we get is a three-dimensional network of reciprocal lattice points, and every reciprocal lattice point in the reciprocal space signifies a particular plane in the direct lattice. So, various reciprocal lattice points are categorized based on their edge indices into equidistant parallel layers, and these layers were perpendicular to x-axis. We expand it along y and z, and then the points are arranged with a translational periodicity in 3 independent directions x, y and z as shown here. So, the reciprocal lattice points which are marked here as star, these points on that particular layer has L index 0. The points which are falling on this plane, that means all those points correspond to H index 0, and similarly all the points which are falling in this region are having the K indices 0, and then all these correspond to a 3-dimensional network very similar to the one in the direct space. So let us see what happens if we try to construct the reciprocal lattice for an orthorhombic system. In case of an orthorhombic system, we have A not equal to B not equal to C and alpha equal to beta equal to gamma equal to 90 degree. So, this is the orthorhombic lattice with x pointing this way, y pointing here and z pointing upwards. The edge lengths are A, B and C. So, the plane which is perpendicular to x axis, that is the YZ plane, has a distance, the plane YZ, the D 1 0 0 set of planes are parallel to Y and Z. So, the distance is D100, which is equal to nothing but A. So, 1 by D100 is 1 by A. So, the reciprocal lattice point corresponding to the 100 plane is supposed to be at a distance 1 by A from the origin. So, now if we consider that 1 by A to fall at this point, and then D010 is equal to B, because this is 0 1 0 set of plane. So, the normal from origin to this plane is 0 1 0, which is equal to B, and we chop it at 1 by D010, which is a distance 1 by B. We put a point here, and similarly D001 is the distance of this plane, which is 001 set of planes. So, this is equal to C. So, 1 by D001 is nothing but 1 by C. So we chop it at a distance 1 by c. So if we now try to draw the corresponding lattice connecting these three sets of points, what we would get is a reciprocal unit cell as is drawn here. So this is the reciprocal unit cell for this orthorhombic system. So in this case, the reciprocal lattice distance A star is equal to 1 by A, B star is equal to 1 by B, C star is equal to 1 by C, and reciprocal lattice volume is equal to 1 by V, which is equal to 1 by ABC. So for crystal systems where you have these angles 90 degree, it is very easy to construct the reciprocal lattice as I have shown in this presentation. So today in this lecture we have learned how to generate what is a reciprocal lattice, what are reciprocal lattice points, and how to construct a reciprocal lattice for a crystal system with the angles equal to 90 degree. In the next class we will discuss about the reciprocal lattice for a triclinic unit cell.